Now in chapter 6, we're going through normal probability distributions. We have touched on these before. We're getting a lot more in depth now in chapter 6. As you look at the syllabus, you may notice that exam 3 is only on chapter 6 because we're covering 6 sections in chapter 6. 6.1 is on the standard normal distribution. Some key concepts in 6.1. We're going to cover these standard normal distributions in detail. These standard normal distributions have the following 3 properties. Number 1 is that they're bell-shaped. Number 2 is that the mean, or mu, the population mean, is equal to 0. Number 3, sigma, the standard deviation for a population, is equal to 1. So those are the 3 requirements for a standard normal distribution. In 6.1 specifically, we're going to be able to find the area, where the area is equivalent to the probability or relative frequency corresponding to various regions under the graph of a standard normal distribution. Here we will also find z-scores, which correspond to the areas under the graph. If you need a refresher on z-scores, check back in 3.3 where we practice calculating those. So we cover the 3 requirements. Now to define a normal distribution. If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, we say that it has a normal distribution. A couple important details here. Our variable has to be continuous rather than discrete, and that it has to be a random variable. Remember that for random variables, they have to be a single value for x, and they're determined by chance for each outcome of a procedure. An example then of this symmetric and bell-shaped would look something like this. So we have our mean value here on the x-axis, or mu. Then this curve is also bell-shaped. It's also symmetric because this side is a mirror image of this side of the graph, so it has symmetry to it. Now, as you know, for graphs, we can have an equation to describe the curve of a graph. The equation for a graph that has a normal distribution is a little bit more complicated than just a straight line, so y equals mx plus b. Here for a normal distribution, it's this, where y is our vertical variable here, so on the y-axis, x is the horizontal variable here, so on the x-axis. So here's y in the equation, here's x. Mu is the population mean, as you know. Lowercase sigma is the population standard deviation, also as you know. Now the other components here, this is a constant e, so e to the power of all of this. This is a function that's in your calculator. This e relates to logarithms, more specifically it relates to natural logarithms. You're going to want to compute all of this here first, and then take e to the power of all of this. The other component here is pi. That's the constant that you're used to seeing, or 3.14159. In your calculator, there should also be a pi button, depending on what type of calculator you have. When you use that pi button, it will include more decimal points than just 3.14. So it's recommended for better accuracy, you'd actually type in pi if you were to solve an equation like this. There's also a way, of course, to use Excel to get e to the power of this. There's also a pi function in Excel as well. Here's some additional examples of normal distributions. You've seen something like this before, so if you want to go back to 3.2 to get a refresher on this empirical rule of data with a bell-shaped or normal distribution, it's essentially telling us how much of our data is going to fall between -1 standard deviation and +1 standard deviation, which that percentage of data is about 68.27. This 95.45 will tell us the percentage of data that will fall between the mean -2 standard deviations and the mean +2 standard deviations. Then, based on this percentage here, about 99.73% of all of our data, if we have a normal distribution, will fall between the mean -3 standard deviations and the mean +3 standard deviations. Another interesting way to look at these normal distributions is to see the impact of the variance value. Remember that variance is sigma squared, so these are all variance values. It's difficult to tell here with this all in black and white, but the pattern here is that the smaller the variance value, the thinner the spread is of the curve. So for example, for a variance of 1 over 32, it would be this very thin distribution here. So 1 over 32 is a small number. 1 over 2 would be 0.5. That's greater than 1 over 32. So for a variance value of 1/2, it's going to be a wider spread for the normal distribution. So ultimately, as the variance value increases, the wider the spread is here for a normal distribution. And right, that makes sense because we think about what the variance means or what the standard deviation means, and it's how far each one of our variables of x is from the mean value. So for a relatively larger variance here, like 1/2, it's going to be a wide spread of the data. For a relatively smaller variance value here, like 1 over 32, it's going to be a thinner spread of the data. And just so you know, the value of 1 over 32 is about 0.031. So then 0.031 is definitely less than 0.5. The next topic here in 6.1 is uniform distributions. Let's talk about the properties here. So for a uniform distribution, number 1, the area under the graph of a continuous probability distribution is equal to exactly 1. Number 2, there's a correspondence between the area under the curve and the probability. So probabilities can be found by identifying the corresponding areas in the graph, and then using the area for a rectangle, which is area is equal to the height times the width. Next, to define a uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The reason we can do this math here of height times width is equal to area, which is the formula for a rectangle or a square specifically, is because the graph of a uniform distribution results in a rectangular shape. There's an example of this in your student outline. We'll also look at the shape of a uniform distribution in 2 slides from now. Okay, so before that, we want to get into density curves. Density curves are sort of a subsect of uniform distributions. So the graph of any continuous probability is called a density curve specifically, where any density curve must satisfy the requirement that the total area under the curve is exactly 1. Now for density curves, we can still have a curve to the data. This is because for density curves specifically, the area under the curve has to be 1. The difference here between density curves and uniform distributions is that uniform distributions have a flat line for their curve. We'll look at that on the next slide. So because density curves are sort of a subsect of uniform distributions, this principle still holds true. So because the total area under any density curve is equal to 1, there's a correspondence between area and probability. How do we know that? Well, we know from our probability section that those probability values can span from 0 to 1 or 0 to 100%. So if the area itself all adds up to 1, then we can make correlations between the area under the curve and the actual probability values. That is only because this whole area adds up to exactly 1. Now, here's a great example of a uniform distribution. For uniform distributions, as we know, the area under the curve also has to add up to 1. And importantly, beyond that, this distribution here, this line, has to be uniform. It has to be flat. So you can easily recognize uniform distributions because the distribution will actually look like a rectangle like this. Let's look at this example now. So during certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 and 5 minutes. This isn't illustrated on the next page, it's illustrated right here below. Let's go through the properties of uniform distributions first. So looking at this graph, it's important to recognize that all the different possible waiting times are equally likely to occur. How can we recognize that? Well, if we see this wording of equally likely, we should automatically think, okay, then they have the same probability. So each of these waiting times, 0 through 5 minutes, they all have a probability of 0.2. That means they're all equally likely to occur. Another important property is that for uniform distributions, they have to be continuous random variables. Remember what the meaning of continuous is here. So these waiting times can be any value between 0 and 5 minutes, not just the discrete value of 1 minute, not just a discrete value of 2 minutes. The variables here, importantly, are continuous. That means that even 1.2, 3, 4, 5, 6, 7, 8, as many decimal points as we can go out to infinity decimal points, that's a possible variable because we're dealing with a continuous set of data. Another important property here, if we were not given this probability is equal to 0.2, we could figure that out. So remember our requirements that each of these outcomes has to be equally likely to occur. Also importantly, for a uniform distribution, the area under the curve has to be equal to exactly 1. So if we were not given 0.2, we could figure this out. So again, by assigning the probability of 0.2 to this height of the vertical line, it makes this area exactly 1. How would we figure that out on our own if we weren't given this value of 0.2? Well, that probability value here that establishes the height of this vertical line, so this is 0.2 probability in height, we get that 0.2 by taking the range. So remember what the range is. It's going to be our maximum data point minus our minimum data point. Here, this is 5 minus 0, so our range is 5. Then to find that probability, we're going to take 1 over the value of the range. So 1 over 5 is equal to 0.2. That's how we would get this probability value if it were not given to us. Okay, so far we recognize this as being a uniform distribution. The area under the curve is exactly equal to 1. These continuous variables all have an equally likely outcome of 0.2. Now let's try this. So given the uniform distribution illustrated here, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. Important wording here, has a waiting time of at least 2 minutes. What does that at least mean? It means that the waiting time could be 2 minutes or any other time beyond that, up through 5 minutes total. So here's our solution. We're going to denote a line here so the waiting time can be exactly equal to 2 minutes or anything beyond that, up to a total of 5 minutes, right? So all of this shaded region represents the probability that we want to figure out. Because so conveniently for uniform distributions, this whole area is equal to 1, we can figure out the area of just our shaded region. To use our notation for probabilities that you should always keep in mind and always remember, so capital P, the probability of a wait time of at least 2 minutes. So with this probability notation, how we solve that is we take the height times the width in this shaded region, and then we get our probability value. Well, the height is the same for all of our variables, so the height is 0.2. The width in this case would be from 5 to 4 to 3 to 2. So our width is 3, so 5 minus 2. That means the area under the curve, or then the probability of a wait time of at least 2 minutes, is 0.2, the height, times 3, which is the width. So we get an answer here of 0.6. So here's our answer. The probability of randomly selecting a passenger with a waiting time of at least 2 minutes is equal to 0.6. Okay, so we were introduced to standard normal distributions. We also went through uniform distributions. And part of uniform distributions, we touched on density curves. Now we're going to come back to these standard normal distributions. So if you went back to refresh yourself on z-scores, you would see that we ended up adjusting our data to fit these standards of a standard normal distribution. So when a distribution is a standard normal distribution, then it's going to fit into these parameters already. So a mean is equal to 0 and a standard deviation is equal to 1. If you went back and refreshed yourself, you'd see that we had a mean and a standard deviation value other than 0 and 1, and we adjusted our value in order to get a z-score. Here, because we're talking about these distributions themselves, the mean is equal to 0 already, and the standard deviation is equal to 1. Now, importantly here, the total area under this density curve is also equal to 1. For a uniform distribution, it was fairly straightforward to figure out the area under that curve because this was a flat line here. For standard normal distributions, this curve is bell-shaped. So it's going to be a little bit more complicated to figure out the area under a curve like this. It's not just a straightforward height times width equation. But we can still do this because the area under the curve does total up to 1. Now, although it's a little bit more complicated to do this, we have technology and we have a table in the back of our book. So we can find areas, which when we say areas, that's the same thing as saying the probability. So we can find areas / probabilities for different regions under a normal distribution curve using either Excel or Table A2. Now, Table A2 is a totally fine way of doing this. Rather than using A2, I do recommend you use Excel. Remember, Excel is our friend. I know next time I go onto campus, I'll see a lot of you wearing these shirts because you've also found this true love for Excel like I have. Now, we're going to talk about using both Table A2 and Excel. So in using Table A2, it's really essential to understand the following. Very importantly, Table A2 is designed only for standard normal distributions. Remember how we know if something is a standard normal distribution? It's going to have that bell shape. It's going to be symmetric as far as the curve. It's also going to have a mean of 0 and a standard deviation of 1. Next, there are two different pages for Table A2. The left-hand page, or page 734, is for negative z-scores. The right-hand page, or page 735, depending on what version of the textbook you're using, this has the positive z-scores. We will do an example of all this. So then the next point here is that each value in the body of the table is a cumulative area from the left. If you remember this meaning of cumulative, we talked about this recently in chapter 5. So each value in this table A2 is a cumulative area from the left up to a vertical boundary above a specific z-score. I'll talk a lot more about what I mean by this. You can already start to see it here. So cumulative area from the left, that means that this whole area here up to our z-score value. Similarly, for positive z-scores, it's this whole area here to the left in a cumulative fashion, so it's all these different possibilities together up to this z-score. So when using Table A2, it's always the cumulative area from the left up to some vertical boundary above a z-score. That'll be really important as we're actually doing problems with this. Okay, still continuing on talking about how to use Table A2. So number 4. When working with a graph, avoid confusion between the z-score itself and the area. Remember, you can always go back and get a refresher on z-scores because we've talked about these before. So now for chapter 6.1 specifically, z-scores, it's the distance along the horizontal scale of a standard normal distribution, and it corresponds to the number of standard deviations above or below the mean. In Table A2, the z-scores are on the leftmost column and at the top row in that table. Again, we will do an example using the table. So that was z-score. Now for the area, it's the region under the curve. The area values in Table A2, they're going to be in the body of that table. Number 5, the part of the z-score denoting the hundredths place is found across the top row of that table. We will do an example looking at this as well. So in this far left column, You're going to see some digit here, some digit in the tenths place. Once you've located that, you're going to go across the top row here then to find the correct digit that's in the hundredths place. Remember for decimals, that terminology, you could have 1.57, where the 5 would be in the tenths place, the 7 would be in the hundredths place. Now, really importantly, depending on which technology you use, you'll get a different area for a given z-score. Not just a slightly different value, but a different meaning of area. For example, with some common technologies, you might get a cumulative area from the left, as we just talked about with the table. You could also be given an area between two boundaries. We'll talk about that as well. We'll also go through this third bullet point. So some tables, not usually technology, will report the area from the mean to the z-score. So essentially the takeaway from this slide is that depending on what technology you use, you need to be clear on what value you're getting. What's the meaning of that value? Now, if the meaning of that value is the cumulative area from the left, as we talked about for table A2, that means that we're getting this cumulative area here from the left-hand side of the curve all the way up through some specified value of z, our z-score. This format is the one you'll likely get the most used to seeing. You'll get this format, this cumulative area from the left up to a given z-score using table A2 in the textbook and using Excel. These should be the two main ways you're approaching questions like these, so you should be getting a cumulative area from the left. There's some other technologies out there like StatDisk, Minitab, and StatCrunch. These are all sort of slightly different versions of Excel. The other way you might get this data presented to you is an area between two boundaries, so from a lower boundary to an upper boundary. To get an answer in this format, so this lower boundary to an upper boundary, it means you're going to be using either a TI-83 or TI-84 Plus, or even a more advanced calculator than one of these from Texas Instruments, or you're using StatCrunch. If you're using one of these types of calculators for questions like this on an exam or on the final, I highly caution you to remember what value you're actually going to be getting from that calculation. You always know to be safe, you could use Excel or table A2 instead to get that cumulative area from the left. That's what I recommend doing for cases like these. Now, there is one other format I mentioned that can come from a table. So some tables will report the area from the mean to the z-score. It's really crucial that you look and see what technology you're using, what table you're using, and see what value is being reported. You know to be safe to get the cumulative area to the left, you can always use Excel and table A2. Let's do an example here with bone density. In the health field, a bone mineral density test can give us information about a patient and if they might be experiencing osteoporosis. So getting small pores or holes in their bones due to a different myriad of health reasons. Now, the result of a bone density test is commonly measured as a z-score, it turns out. The population of z-scores is normally distributed with a mean value of 0 and a standard deviation of 1. So we can check off these requirements that the results of these bone density tests meet the requirements of a standard normal distribution. This graph here, for example, shows the bone density test scores. Notice that this is bell-shaped, this is symmetric, we have a mean value of 0, and then along our x-axis, our horizontal axis, is where we're going to look at the z-scores. These z-scores will then correspond with some area under the curve. So here's our question. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score less than 1.27. That 1.27 value, that's our z-score itself. So in this scenario, because bone density scores follow a normal distribution like this, then we can equate the bone density score itself to a z-score. Let's go through the solution now. So number one, note the following are the same because of the aforementioned correspondence between probability, and area. In the question, we're asked the probability that the bone density test score is less than 1.27. Now, remembering this correspondence, this connection between probability and area, we have our z-score or our bone density test score of 1.27. We want to find the probability that the bone density test score is less than 1.27. It can be any value less than 1.27. As far as area now, this shaded area under the curve, under the normal distribution, if we find that value of the area is going to be our probability. Why? Remember that probability values all add up to 1, just as the area under this curve all adds up to 1. So if we find the area under the curve here up to a z-score of 1.27, then we'll have our probability value. Okay, so as mentioned, we need to find the area in this figure here, where z is equal to 1.27. We need to find this area here, cumulative to the left. We're always going to be talking in terms of cumulative to the left. However, this is a more straightforward example because we're asked for the probability that a person has a bone density test score less than 1.27. So the way this question is worded, it matches with how we normally talk about this. So this cumulative area to the left. We'll do an example later on where we'll find the area that's greater than a certain z-score, and we'll talk about how to approach that. Okay, so continuing on with the solution, we're going to use Excel. For these standard normal distributions, we can use the function in Excel as capital NORM period DIST. So normal distribution is what it stands for. Keep in mind that Excel works the same way as that table. In other words, when we use Excel, we're going to be finding the cumulative area from the left up to a certain z-score. So we should get used to just thinking in this way. So some cumulative area to the left up to a certain z-score. That's going to give us the probability or the area of getting a variable less than a certain z-score. Again, keep that in mind because we'll talk about how to approach a question when we're asked about some area greater than our given z-score. How do we do this specifically in Excel? Well, I recommend setting up a table like this. So we're going to have our z-score. That's the same thing as our x value in Excel. Keep that in mind. So our z-score or our x value here on the x-axis is where we get our z-scores. That's one way to remember that. So we need our z-score slash our x value. Here, that z-score is 1.27. That value comes first, then comma, the mean. Remember, for a normal distribution, that value for the mean is always 0. The next value here, so comma, this value, that's our standard deviation value. Remember, for a normal distribution, the standard deviation value is always equal to 1. So for normal distribution problems, this will always be 0, our mean. This will always be 1, our standard deviation. Now, the last value here is this cumulative value. You've seen this idea before as well. Here we want a cumulative value of 1 because we want to know the area for all of these values less than 1.27. Not just the area here of 1.27. It'd be some infinitesimally small sliver of area. So we're going to use a cumulative value of 1. You don't have to set up a table like this. You can also just type these numbers in. So equal sign to start a function, NORM period DIST, open parentheses, 1.27 for our x or our z value, comma, 0 for the mean, comma, 1 for the standard deviation, comma, 1 for the cumulative value. I like doing these formulas in the cells themselves. You know, you can also prompt for this function box to pop up and then type in your values this way. So continuing on here, we want the area below 1.27 because we're asked specifically the probability that this person has a bone density test score less than 1.27. We can use Excel, we can use table A2. Keep in mind, both of these will give us our cumulative area from the left. Here, that's what we want. So the desired area is 0.8980. We get this value here, and it was just rounded off. So now we know this area under the curve less than 1.27 is equal to 0.8980. Because of the correspondence, the connection between area and probability, we can say then that the probability of a z-score below 1.27 is 0.8980. Okay, so we used Excel, we used the best way to do it. Let's also use this other way of doing it using table A2. Using table A2, first we need to recognize, again, this is 1.27, this is our z-score. 1.27 here is a positive value. The first thing to do is decide, is your z-score a positive or a negative value? If it's a positive value like it is, we're going to go to page 735, where it's labeled positive z-scores. To then find our z-score of 1.27, we're first going to look at this digit and then the digit in the tenths place, so 1.2. We go on this left-hand column to 1.2. Next, we go over to whatever value is in our hundredths place. Here, 1.2, then 7 is the digit in the hundredths place. So we first found 1.2, then we go over to 0.07 because that's the value in our hundredths place. Then remember, for this table A2, we're going to be finding the cumulative area to the left. For a z-score of 1.27, we get an area, therefore a probability value of 0.8980. That is the same answer we got using Excel. That's what we expect to get. Okay, so using table A2, first we decided positive z-score or negative z-score. We went to the page for the positive z-scores. We found 1.2 here in this column. Then because our z-score is 1.27, then we go 1.2, we find the correct digit in the hundredths place, and then we find our corresponding area or probability value. Importantly, this first column is part of the z-score. This first row is also part of the z-score. Then the body of the table here are the corresponding area, or therefore probability values. Also importantly, of course, this area or probability value refers to the cumulative area from the left. Okay, so we used Excel, we used table A2. We're getting more comfortable with both methods. Let's also talk about how we interpret that probability value. So the probability that a randomly selected person has a bone density test result below 1.27 is 0.8980. This probability value is correlated with the value of the area under the curve, or this shaded region here. Remember that probabilities can go from 0 to 1 or 0 to 100%. So another way to think about this is that 89.80% of people have a bone density level below 1.27. How do we go from a number into a percentage? We multiply by 100.